Hello again. Last time we talked a lot about work, power, mechanical advantage, and levers. Remember, there are 6 total simple machines, and we'll concentrate on the other 5 this time. You see on the screen wheels and axles, inclined planes, but there are also a couple more that we will mention as well. So get ready for sections 13, C, and D, mainly simple machines. Here we go. All right, what is a wheel and axle? Well, obviously we know what a wheel is. See the guy riding the bike. He is pushing on the pedals, and the pedals are attached to a small wheel that's attached to a chain, that's attached to another small wheel, that's attached to larger wheels. But what do the wheels turn around? Remember that a lever is a bar that turns around a fixed point we call the fulcrum. Well, think of a wheel as a lever that goes all the way around, and we call the fulcrum an axle. So wheels and axles are actually levers that go all the way around. And the picture, the words are a little fuzzy, but you're looking at a steering wheel for a car and the wheels attached to an axle as well. A lever that goes all the way around, such as in a tire, that's what a wheel is. And the center is the axle, the pivot point, the fulcrum, but in a wheel and axle, we call that fulcrum an axle. Now, here it gets a little confusing. Mechanical advantage. We want, in most machines, our mechanical advantage to be greater than 1 because that's going to multiply a small amount of force. Well, that's not always the case, especially in something like a 10-speed bike. If you've ever ridden a 10-speed bike, you will notice that the lower gears, lower numbered gears, they're easier to pedal, but the bike doesn't quite move as fast. But put those gears into higher levels, gears 8, 9, and 10. Those are the hardest to actually pedal, but then the bike moves a whole lot faster. Our mechanical advantage may be less than 1 in some cases, such as on a bike, but realize the larger wheels go further distances, and the larger the wheel, the bigger the diameter, the more distance one complete rotation will be. So think now of a car tire, a smaller axle, as you see right about here, and a much larger wheel in diameter in comparison. As the axle pivots at one central point, well, take a look at what the wheel does. Let's consider this point right here. This point is going to travel all the way around at a much greater circumference, which is a distance, than this pivot point where the axle is. And the larger the wheel, the more distance. That's common sense, but scientifically speaking, that really should make sense. If our mechanical advantage is greater than 1, that means we have a multiplying force, like the steering wheel will do. But remember, the steering wheel will turn a lot more than the axle. So if we grab the steering wheel at around this point here and start to turn, that circumference, one complete rotation, is going to be a lot more than that pivot point right there. That's going to cause the tires to turn. And then the tires, as we said a moment ago, they're going to make a complete revolution. The bigger the tire, the more distance. So even though we still have a mechanical advantage, which may be less than 1, we do have an advantage, and that will go further distance with that mechanical advantage, not really multiplying the force all that much. And that's going to happen. Now he's going to push down on the bike, not completely straight down, but sort of in a circular pattern. And we have what's kind of like a pulley right here. We'll explain pulleys in a few minutes. With the axle here, that's connected to the bike tire. And the bigger the bike tire, the more distance that bike will go in one complete rotation, which should make sense. So wheels and axles. Will also keep something else in mind. Why do we put heavy objects on carts with wheels? Well, if we have a very heavy box full of books maybe, that box would have a lot of weight and a lot of surface area scraping against the floor if we try to push something across the floor. Of course, carrying a heavy box, well, it might be hard to lift a lot of weight. But putting that box on a cart, well, when we do that, the cart has only a few points of contact with the floor, so there's much, much less friction involved. And therefore, as the wheels turn, very little resistant forces. That's why we can put something heavy on a cart and use that cart to move the object with much, much less effort. So wheels and axles, very useful, simple machines. Ready? Now think of gears, like on a 10-speed bike. Okay, gears can be put together in a couple of different ways. A small gear that will end up turning a large one, or a larger gear that will end up turning a smaller gear. And as you see on the arrows, as one turns one way, the other will turn in the opposite direction. And you may have a whole series of gears that will alternate directions on which each gear turns. Now, how are these advantageous for us? Gears use rotational motion to make other essential rotating parts actually do their rotation. Now the teeth, though, that's where the little grooves in the gears. In order for the gears to work correctly, the teeth have to be the same size on each gear. Now the diameter and circumference can be different sizes, but the teeth right there, those have to be the same size. If not, then those teeth won't mesh together. So one tooth here is going to push on the other tooth here. So we have one pushing clockwise, pushing down counterclockwise to the other, and there could be another one that's being forced to rotate in that direction as well. If a small gear turns large, like in the top picture, then we have a force multiplier. So anytime we have a small gear pushing a large gear, we get a mechanical advantage greater than 1, but then for a shorter distance, because this gear is going to have a shorter rotation. This may take 2 or 3 complete rotations for the large gear to turn exactly 1 time. However, we are increasing the effort force. We'll have a mechanical advantage greater than 1. Now look at the bottom picture. When the larger gear turns the smaller gear, we have a force reducer. The MA is going to be less than 1. 1 complete rotation of the large gear, depending on the ratio of the sizes, maybe 2, 3, or 4 rotations of the smaller gear, that's going to reduce the mechanical advantage. In the ideal mechanical advantage, we simply divide the teeth in the first gear, whether first is larger or smaller, turning the second gear, that would be the teeth out. That would be the ideal mechanical advantage, but again, there's friction involved as well. So it's not exactly realistic. The actual mechanical advantage would be, because that accounts a little bit for friction. Ready? Now let's look at a pulley. And we have a heavy object that we need to lift straight up, maybe to get to the treehouse here. We got the weight that needs to get up this high off the floor. We're going to pull on this rope. Now, we have only one pulley, one wheel right here, and a section of rope. And remember, the rope actually goes all the way through. Now, if we pull straight down, then the point of contact is probably going to be right up in here where the rope hits the wheel the most. But most people don't pull straight down. We get a little bit of a diagonal pull. So maybe a little bit more realistically like this. That means the point of contact is going to be about here. Okay? And that could be very important. The pulley is going to help us lift this weight up, because when we pull down on the rope, we're working with gravity. We have resistance here that will push up as we pull down and allow us to turn this wheel here and lift the object straight up. We have the effort arm and the resistance arm being the same length. So let's put that back up here. The point of contact would be right around this area here, because again, it's probably not going to be perfectly straight down. So let's go ahead and fill this in. That means the distance on the resistance side is going to equal the distance on the effort side. They're going to be equal. We're talking about the length of the rope on each side of the contact point. That means the force we get to apply is going to be the same as the force of resistance. So what we will have is a mechanical advantage that's equal to 1, because remember, mechanical advantage is resistance over effort, and if they're equal, we're going to get an answer of 1. So mechanical advantage is only 1. How does this help us lift more easily? Said a few moments ago. We get to pull down and work with gravity rather than trying to lift straight up and going against gravity. The mechanical advantage is 1. The same effort and the resistance length will mean the same effort and resistance force. So whether I did the mechanical advantage by distances or by forces, for distances it would be effort over resistance, for forces it would be resistance over effort, I'm going to get 1 because either way, the effort side and the resistance side are going to have the same value. Units will cancel. Remember, no unit for mechanical advantage. A single pulley will change only the direction of the force, but again, we get to pull down and work with gravity instead of trying to pull up and fight gravity. Now, there really is friction involved right up in here, so it's not exactly 1. Remember, our equations disregard friction. We do actually have to pull a teeny tiny bit harder with effort force than the resistance really is. But a single fixed pulley, a mechanical advantage of 1, still helps us lift a heavy weight straight up. Ready? Now, what about movable pulley here? Now, let's see. We have 2 pulleys here. One here, one here. Now, follow the rope. Now, really, it is 1 rope, but if we look carefully, we'll see, different sections of the rope. We're going to pull right here. And let's say we pull down and we move that a distance of 2 meters. So that would be a pretty high pulley way up. This weight here is actually going to move approximately 1 meter. How is that advantageous to us? You'll see when we see the math up there in a moment. The mechanical advantage is going to be 2, and that's because the resistance and the effort, we get to use half the effort force needed to lift the weight. And that's because of the distances that these things are moving. The distance of the effort we had up here a moment ago, 2 meters, that is the distance of the effort. The weight will move up about 1 meter. That's the distance of the resistance. And remember, when we're talking the distances, the mechanical advantage is the distance of the effort over the distance of the resistance. In this case, 2 meters over 1 meter. Units cancel. The MA is 2. So if we can attach 2 pulleys, one fixed up here that's not going to move, and run the rope, as you see, along here, then we can pull this down with half the effort needed to lift the weight. Therefore, if this weight was 100 newtons, we would get to use only 50 newtons of effort. And let's do mechanical advantage using the forces now. Remember, that's the force of resistance over the force of effort, assuming I can write neatly. That's now going to be 100 newtons is the weight we lifted, 50 newtons is the force with which we lifted. Newtons cancel, we still get 2. So whether we use the distances or the efforts, calculating those correctly will give us a mechanical advantage of 2 with a single movable pulley. The pulley moves half the distance of the pull on the rope. The weight will move up half the distance of the rope that we actually pull. And that's going to allow a mechanical advantage of 2. So using an extra pulley makes the work easier to do by increasing the mechanical advantage. And it turns out the more pulleys we use, the higher the mechanical advantage, the easier it is to lift the object. Ready? A block and tackle. Now here you see 4 pulleys and you see 4 sections of rope in between the pulleys. In normal conversation we say 4 ropes, but again it really is 1 rope, but 4 sections of it. Let's take a look here. Let's say that we use 20 newtons of force on the effort. So our force of effort is 20 newtons. And we're going to pull down here. Well, realize once we extend this rope and get tight tension on here, here's our 20 newtons. This section here will also have that same 20 newtons. Go through the pulley. This section here will also have 20 newtons. This section here will also have 20 newtons, and this section here will also have 20 newtons of tension. Tension is a force. So what we did is we took our effort force applied to each section of rope that's in between the pulleys, And that 20 newtons, we now have 4 times. That is going to take our effort and multiply that effort by 4 because there are 4 ropes and 4 pulleys. So we could then lift as much as 80 newtons with only 20 newtons of force. Multiple pulleys are connected together with the same rope or chain, could be a chain. The more distance of the rope, the less effort force needed. Now remember the distance principle. Since the rope would have to be long enough to go through 4 pulleys, that will allow us to use less pull force on each pull, but we're pulling more rope through those pulleys. So the distance principle applies here to pulleys as well. In order to use less force, we have to apply that smaller force over longer distances. Inclined planes are really going to show that even better. The mechanical advantage is the number of rope segments. Each segment has the same force as the effort, as I showed you a moment ago. Now let's increase our weight to 400 newtons, which is a little less than 100 pounds. Okay. Now how much effort would we need? Since we're able to lift 400 newtons with 1, 2, 3, 4 segments of rope, then our force of effort is actually going to be 1/4 of that 400 newtons. That's going to allow us to use only 100 newtons, which is around 22 pounds of force to lift 400 newtons, which is around 90 pounds actually. And that's because our 100 newtons of force is also here, 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 and here. All these are newtons. We have a mechanical advantage of 4 because we have 4 pulleys and ropes. 4 pulleys gives us 4 rope segments in between the pulleys. The same force that we apply is put onto each section of rope, disregarding friction. We get a mechanical advantage of 4. Now what if we used 6 pulleys and 6 ropes, and it could be 3 up top, 3 on bottom as well? Well, that would be a mechanical advantage of 6. So if we used 100 newtons of effort force, we could lift as much as 600 newtons of weight. The more pulleys we use, the bigger the mechanical advantage. Ready? Let's say we have a piano. We have to get up to the penthouse. You just signed your big contract for big money. You got a penthouse. You want to move that piano up. Won't go up the stairs, too big, won't fit in the elevator. So we need to use pulleys to get that up to the penthouse. Raise a 2,400 Newton piano with a 6 pulley block and tackle. What is the mechanical advantage and how much effort? All right, let's clear these last 2 lines off so we can do the math now. Remember that mechanical advantage equals the force of resistance over the force of effort. Raise a 2,400 Newton piano, that is your force of resistance, with a 6 pulley block and tackle. That means your mechanical advantage is 6. How much effort? Now that we see where to put the numbers, let's put them in place. The mechanical advantage is 6. We are lifting 2,400 newtons. How much effort? Well, in this case, our variable's on the bottom. We just do a little switcheroo trick. Anytime, and I mean anytime, that variable is on the bottom, these 2 numbers can switch places. Let's come over here now and finish. That means I'm going to move over here to have some more room. My force of effort is now 2,400 newtons divided by 6. Remember, there's no unit for mechanical advantage, but we're calculating a force. That means when we do this division, we get 400. There's nothing to cancel that in right now. And remember that Newton is the unit of force. So we did this correctly. If we know any 2 of the numbers, we can figure out the third. How much effort? We just did 400 newtons of force. Ready? All right, an inclined plane. Fancy word for ramp. Walk up a ramp. Allow a lighter force, but again, over a longer distance. All right. I'll exaggerate the drawings here just to show you a little common sense. Okay, we need to get a heavy object like a refrigerator onto the truck bed right there. Little common sense. Which would be easier? Oh, that's bad. Let's try that again. Assuming this is the same height as what I'm going for, and I use a longer but less steep ramp to get that refrigerator onto the truck bed. Common sense will tell us. Hopefully you can see that okay. It's going to be easier to go up the longer, flatter ramp. Mathematics, though, will verify the common sense. All right? Now I look at that, and it may not be that easy to see with the yellow, so let's change this. Okay, there's your refrigerator. You're having to get on the truck. There's the same truck with a longer ramp, so the bed's the same height. And there's your refrigerator. So this height is equal to this height, assuming I drew correctly. Common sense will tell us this is a lot easier, but we have to take more steps and go a longer distance. Less effort, but a longer distance than the top one here. So mathematically it works out. Remember that work equals force times distance if we're going straight up. But how many people are going to lift a refrigerator straight up onto that truck bed? If we're able to, let's say the refrigerator weighs 600 newtons. Now 32 meters is a very high, that wouldn't be a truck bed. But think of building the pyramids way back in the ancient times. 32 meters, you're talking close to 100 feet high. So they had to use a ramp to get all those big blocks up into place. They didn't have the heavy machinery that we use today. 6,000 newtons going 32 meters up high, do the math, 192,000 joules of work. That's if we lifted that block straight up. Now let's use a ramp that's 384 meters long. So how much effort force is needed? Well, in this part right here, we're going straight up 32 meters and raising 6,000 newtons. Now, this isn't going to be drawn to scale, but remember, no matter how long the ramp is, the block's going to end up 32 meters high, way out here, assuming I draw well, for a distance of 384 meters. How much effort will it take to move that big block up this ramp right here? Let's do the math. We have 192,000 joules of work, and remember, conservation means no matter which method we use, if we used pulleys to go straight up, or we used the ramp on wheels on a cart to go up that ramp, we're going to do 192,000 joules of work. So there, the same amount of work. This time we're calculating the force of effort. Just divide here. We get 500 newtons. 500 newtons is a whole lot less than 6,000. In fact, if we calculate the mechanical advantage, force of resistance over force of effort, 6,000 over 5,000 is 12. Or if we use the distances, distance effort divided by distance of the resistance, 384 divided by 32 is still 12. So whichever method we use, we're going to do the same amount of work, 192,000 joules in this case, but one way is going to be a lot easier. In that case, the ramp is going to be a lot easier than lifting something straight up. Ready? All this is coming in practice problems. Here we see the cart being pushed up the flatter, longer ramp and the steeper, shorter ramp. Common sense will tell us which one will be easier to push that cart up. Upcoming lab activities, though, you'll get to see and feel the difference for yourself. Common sense is going to tell us that flatter ramp right there is a lot easier. Now, also notice that we have more support to help fight gravity, much less support. Gravity is going to pull down, so this cart's going to go down that steeper ramp a lot more easily than right here. We'll be able to fight that gravity and push up the ramp more easily. Less effort force requires more distance. That flatter ramp is a longer distance, less effort needed. Less distance requires more force. So assuming those two heights were the same, the steeper ramp is going to be shorter in length, slant height, however, very difficult to push up a steeper ramp. So you want to have a force out that's greater than your force in for high mechanical advantage, or you want to have a lower effort force and a greater resistant force. That's your out resistance, your effort is in, and do the division and get a mechanical advantage greater than 1. The bigger the mechanical advantage, the better the machine. So the longer and flatter the ramp, the easier it is to get up. Now think of people in wheelchairs who can't go up the stairs. So the entryways into buildings have ramps as well. Imagine having to go up the steep, short ramp. That's why the ramps are long and less steep. Now there may be some that go up for a bit, turn and go up for a bit, and turn and go up for a bit again, but if you were to stretch that out completely straight, it would be a much longer distance. Common sense, but the math verifies the common sense. Ready? Okay, wedges and screws. You see the guy chopping down the tree? All right, he's using a wedge. What's the purpose of a wedge? To cut through things. That's the main purpose of a wedge. There's another use too. We even say, let's wedge the door open. We stick a triangular piece of wood maybe under the door to hold that door open. But we use wedges to cut through things. Wedges are actually inclined planes back to back, sharpened to help us cut through. So think of scissors. Those are wedges. Screws have two main jobs also. Number one is to hold things together. You screw two boards together when you're building something. Screws can also dig, so construction workers may use very large screws to dig straight down into the dirt, pull out the dirt, and insert something like a telephone pole. So screws hold things together or dig and pull dirt out, or maybe a lot of wood. Okay. Now, what determines the mechanical advantage of a screw? Think of the word pitch. Look over here on the right. On this side, it's so hard to tell in this kind of cartoony picture, but the distance between the threading is called a pitch. Now think of this. If we were to take the threading right here and stretch that out, we would get some kind of an inclined plane up to that post here. So if we have a small pitch, that means less distance in between these pieces right here, we would end up with a longer piece of steel, or whatever the screw's made out of, instead of a pitch that's bigger with more distance, the same post, that would be less. So that would be steeper, this would be longer. This we've already seen has a higher mechanical advantage than this right here, a low mechanical advantage. So we want our pitch to be small. We want the distance to be small between the threading. That means all the threading has more distance, would be easier to turn. Less effort on each turn, but we have to turn more. If we use a small pitch screw, that's less distance, but each turn would be harder to do. So if it's me, I'd rather turn the screw more, but make each turn easier. And then of course we have power screwdrivers, which do the same job, but get that screw into place in less time. That's why we call those tools power tools. Those tools do the same job in less time and require less effort. Ready? Now, the small pitch has a higher mechanical advantage. We want screws with smaller pitches, especially if we have to turn the thing by hand. We don't have a power screwdriver with us. Now ready. Compound machines. Well, just like in grammar, a compound word is two or more words put together as one. A compound sentence is two or more independent clauses put together as one long sentence. A compound machine is two or more simple machines combined into a larger machine. And that's most everything we use. Very few times do we use one simple machine to perform a task. Well, if we have multiple machines, how do we get the mechanical advantage? We simply multiply each simple machine's mechanical advantage. Therefore, if one of the machines on your compound machine has an MA of 5 and another has an MA of 2, and let's say there are 3, an MA of 3, 1, 2, 3, well, then the total mechanical advantage of the compound machine would be 5 times 2 times 3, which is simply 30. We just multiply them all. And even if part of that machine has an MA less than 1, which could happen, we'd still multiply, but we're going to get an overall good mechanical advantage. And that's why your big compound machines make things so easy to do, because they're taking smaller mechanical advantages and multiplying them together into one large product. Most of what we use are compound machines, not simple machines. Okay? Which again, common sense. Ready? And there we go. Power up and work hard. Thank you.